have to move that closer.
Is that
And you want to?
okay?
Yeah, hold on.
Full screen, isn't
There.
it? Okay.
We good?
So I'll just give you a
Go
quick
ahead.
intro. All right. So we're live. We are live on the interwebs. Welcome to our pre-Valentine's Day TWED. Thank you all for coming. There's more pizza in the back. I just a logistical reminder that although it's being screencast directly from the laptop, all the audio is being recorded and sent out onto the internet live and also recorded. Just keep that in mind in questions and follow-up discussions in case that's an issue. Also, a reminder, so we have a TWED next week as well. Our cycle is not quite every other week. Sometimes we bunch them together. Our next week's, Amar is going to talk about hacking with jQuery, triple stores, and Sparkle. So it's kind of one of our, sort of an introductory talk on essential technologies that we use throughout the lab. So that should be a good one. Today we're welcoming Timothy Lebo, who is going to talk through, I'll let him do the deep introduction and contextualizations, but Prizms.
Thank you, John.
Let's welcome Tim.
So, good evening. Thank you for coming. Really excited to talk about introduce Prizms and kind of try to convey some of the things that I've been working towards over these past several years with all these tool sets that we've been putting together. And so ultimately what we're striving for is to be able to create better visualizations that are catalyzed by better data. So the outline of tonight's talk really falls into two parts. First I'm going to do just a quick overview of the current core three components that Prizms comprises today. And then once kind of lay that out as a basis, I'd like to try to sketch out some of the other things that I am working towards to build off of the basis that we have today. So the three parts are the converter, data fax, and loudspeaker. And the purpose of the converter, CSV to REF or LOD, is that we are interested in collecting lots of different data from lots of different sources to be able to incorporate that, integrate it into a nice, cohesive, well understood structure using RDF and linked data so that we can get a much broader perspective across all of these individual data sets that they themselves might have multiple revisions. So we want to be able to do this while being limited on time, domain expertise, as well as semantic web expertise. So that's where the converter tries to fill that gap. So ultimately what the converter does is catalogs, organizes, retrieves, converts, and publishes disparate data sets of primarily tabular data, but the automation can handle arbitrary data formats. And it encapsulates all of those commands, all of those activities within a few key executions on the command line. I mean, ultimately, this was intended to just solve the problem, right? I've got lots of data that's not in RDF, and I want to get it into RDF. And this is just one tool among potentially hundreds that are out there that does that same task. But really what this has kind of grown out of and where it shines is its metadata support and its provenance throughout that aggregation and integration process. So I think that's really where the converter stands out among the rest of the community of these tools. And again, this is available on GitHub, like all of the projects that I'll be talking about today. The second component of Prizms is data fax. It's a linked data quality evaluation framework. And really what this grew out of was kind of the end result of creating the converter and applying it to the Linking Open Government Data project that we had here at Catalyzed World. And when you pour a lot of time into a system that makes really great data, or can make really great data, and we produced 10 billion triples for the Linking Open Government Data project by pulling together a lot of the data from data.gov as well as other government sources. The problem still remained that, well, we've got this data and it is integrated and it is connected and has great metadata and provenance, and it's available as linked data. But so what? How do you compare that data to the rest of the available data on the linked data cloud? How do you understand and gain insights into what your consumers are actually interested in when they're using your data? Maybe you think that you did a really great job with how you integrated it and provided metadata and provenance, but maybe your consumer either isn't interested in it or has different expectations for how that data is represented or is available. And so really data facts comes down to this matrix of data sets crossed with evaluation services. And we just have two example data sets here, our LOGD data set from the Linked Data Cloud as well as SiteSeer, right? So if you wanted to compare these two on how good they were doing a job of creating and producing linked data, you could use a variety of evaluation services which are implemented using the SADI framework, so that you essentially just HTTP post a description about LOGD or a description about SiteSeer, feed that to the evaluation service, and it can return back kind of a pass or fail as well as any particular metadata that fulfills that claim that it's good or bad. And so this matrix view on the left allows you, who's interested in a particular subset of data sets, to evaluate using evaluation services that are created by both you as well as other people across the web. And so this view on the right is the kind of the decoupling of the data sets that are available with the evaluation services that you use to evaluate them. And you can compose those for your own purposes for the data curation that you're interested in. So a real example of using data facts. So for the Provenance Working Group at W3C, we're in the process of creating the implementation report because we're in candidate recommendation. In order to get to proposed recommendation, we need to demonstrate interoperability and use of adoption of the provenance data interchange model. And so we're capturing provenance all over the place with both the conversion automation as well as data facts itself. And so here is an example SADI service that I wrote. That's a data facts evaluation service. I'm just hosting it locally, but it's the code's available on GitHub. You can host it through ModPython through Apache, so that you can host it as a legitimate web service. But on the left-hand side is an RDF description of the data set that we're interested in determining whether or not that is using this LOD bubble is using the provenance ontology. And so what we're saying here is we're just analyzing the Melagrid data set, which is a bubble in the LOD cloud. And we're just saying that data set has a data distribution using the DCAT vocabulary to say that it has a Sparkle endpoint at this particular access URL. And so we HTTP post that description about our data set, and we're asking the evaluation service what it thinks about that particular data set, and it returns this RDF description on the right-hand side to say that Melagrid is data facts satisfactory, and it is using the prov vocabulary, and that asserts that using vocabulary of interlinked data vocabulary, as well as a histogram count of each of the terms within Provo and how many times they occur within that triple store, within the access URL that was posted. So just an example of how DataFacts uses SADI and how it uses for a real problem And so you can kind of craft whatever SADI service you're interested in to capture in on whatever particular quality metric you're interested in or wish to convey to anybody across the linked data web. And then just to wrap up data facts, the idea is that you do your individual analysis where your data sets that you care about with the evaluation services that you care about. Other people do that same thing, and then you're creating a data facts network, which is really linked metadata. It's linked data about linked data, and so you have an entirely new layer of linked data to be able to understand the linked data that exists beforehand. Yeah.
I know this isn't an ontology evaluation, but something that comes up in the ontology community is intrinsic and extrinsic evaluation.
Yep.
And how would you categorize this? Would you categorize this as intrinsic or extrinsic, or?
Yeah, so the question is the distinction between intrinsic and extrinsic quality measures for particular data sets, or in this case, ontologies. So really, the any degree of context which allows you to go from intrinsic to extrinsic characterization can be encapsulated within the evaluation service. So if the evaluation service wants to use a particular context in which that ontology should be evaluated, then you would include a description about that context if you wanted to kind of parameterize the evaluation service. Or the evaluation service could just be crafted to encapsulate that context implicitly. So I think it centers around context.
So I think what you're saying is you could use it for either.
Yeah, absolutely. Yep.
And both.
Yes. Okay, so the last part, given that we've pulled together lots of different data sets, made a nice coherent RDF graph out of it, and we're accumulating evaluations from across the web for our own purposes, we have gained better understanding of the data that we have. This third component is Loudspeaker, which is developed by Alvaro Graves, also from Titleist World. His GitHub is at the bottom of the slides here. I just wanted to give a quick sense of my third-party perspective of how Loudspeaker works and why I think it's fantastic. So this yellow box in the middle is Loudspeaker, and where it fits, it kind of lives in Apache and a PHP stack, and you can make web requests both as human agents or computer agents that are requesting different kinds of content types. So here the human's just asking for HTML, the blockhead is requesting RDF XML. And the first thing that happens within Loudspeaker is kind of a model view selection. So based off of the URI that was requested, there's a kind of a decision tree on which model view should be selected. Once you've selected that, the model is just encapsulated by templated Sparkle queries that you can compose across different triple stores. You can actually use the results of previous Sparkle queries to feed in to fire off subsequent Sparkle queries. Once you've executed that, you get the bindings back, and then you select the appropriate view template for the content type that you're trying to return, and then that just returns it back to the user. So you strap this on to a Sparkle endpoint, and any URIs within that that live within your URI space are now linked data, conforms to best practices there, but also allows you to craft the human web views of the different data that you're interested in portraying and walking and crafting a web page around. So I just wanted to give a sense of Prizms in terms of those three components, and I'm going to mention Virtuoso as well. So all of this, the first part of Prizms is really just getting all these things stitched together. And there's a lot of interwiring across these components as far as what URIs are used where, what environments variables are set where. And so I just Googled this progress bar, and it's about, I'd say, around that 80% mark on being done. And so looking forward to having that finished in the next couple of weeks, and then just having all of the concrete components wired together so that we can start moving forward and looking at the stuff that I'm talking about in the second half of this talk. So that's Prizms today. It's basically these three components stitched together. We can pull together data from disparate data sources, create a coherent RDF graph out of it. We can evaluate it from across the web, and we can rehost it both as linked data and human viewable web. And so the rest of the talk, I want to talk about where I envision this going and what I want to do with it. That falls into these three categories, which I'll walk through after I try to motivate it. But before I get started, I'd like to just say that this is completely preliminary. I have kind of pieces hanging around, and it's not ready to be evaluated, but I'm really looking forward to doing that. So, Ben Schneiderman at University of Maryland, back in '96, proposed this task-by-type taxonomy. He proposed 7 tasks that users should fulfill, starting with overview, where one gains an overview of the entire collection. In my animated slides, all of these reds would be blues, but I'm categorizing these 7 different tasks right now according to how well I think that the semantic web is actually fulfilling these tasks. And all of the red means lots of bad. These 4 right here are actually brown, so we're kind of doing it, but not as well as I think that we could be doing it. And so I'm going to be proposing the subsequent half of Prizms to fulfill these requirements. So the overview, I think we're just utterly failing in. An overview of an entire collection. In our sense, just for LOGD, an entire collection is 10 billion. So you multiply that across the rest of the LOD cloud. What is an overview of that? We really don't have one other than the LOD omnigraphal file, which isn't informative enough to lead to anything interesting for the data that you're interested in. The zoom we're kind of doing. If you zoom in on items of interest, if they're already shown to you, then it's pretty straightforward to just look at them. Filtering, we have Sparkle, and that's kind of a cornerstone in every application that we develop, create, so filters kind of handled. Details on demand, well, you can't get any more details on demand than just dereferencing the URI, so that's pretty cool. Relate, view relationships among items, pretty straightforward. History, being able to undo, replay user interactions to reconstruct the particular data that you're showing, and then finally extract, which I think is one of the great powers that the semantic web can offer back to the visualization community. And I don't think that they're doing well at all. So I think there's a lot of opportunity there. So both extracting the sub-collections of the data that you've kind of distilled down to, as well as the query parameters that led to that particular data subset. So here I have the same 7 tasks from overview down to extract, and I'm kind of filling in what I'm envisioning in creating with Prizms to fulfill what I see as the shortcoming in each of these 7 tasks. So for the overview, I want to talk about tonight both the between the edges and the SPO balance overview techniques, which apply to arbitrary RDF graphs. And then I'll also be talking about the data carving, which allows you to create data subselections. For Zoom, I think there's going to be some more work done there, and I'll be talking about visual strategy a little bit at the very end of my talk. Filtering, again, data carving and visual strategy. Details on demand, data carving, visual strategy, but in addition, provenance and backlinks. And so that'll be the very end of my talk. And the relate, history, and extract is being fulfilled by the same core components that I'm proposing to stitch together. So before I dig into each of these 5 or 6 different new parts of Prizms, I'd like to try to contextualize where they're going to fit. All of the 3.5 years of converter work, data facts work, linked data work, I think lives in the that black layer. At that black layer, we're assuming that the graph is coherent. It's well structured. It's using the right appropriate vocabulary, not necessarily the right vocabulary, but it's all right there, right? And so the first half of the talk where I was talking about Prizms is just pulling together all those three pieces. Really, that's where I see Prizms being today. And the rest of it, the data carving, the visual strategy, and the provenance and backlinks are what I'd like to look forward to in the rest of this talk. So, hey, I've got 10 billion triples. Now what? I think that's as simple as I can pose the problem. What do you do to start figuring out what is in there? And my answer is make more triples. So I mentioned this a couple weeks ago when Jim and I presented health data. So I just want to walk you through a transform here. In the upper left, I have Tim Berners-Lee's 212 triples of his FO file. That's the original graph. And if you just extract out the 116 unique URI nodes within that graph, then you just get this list. Here I'm showing 5 example URIs from that FOF graph. And if we just type them to RDFS resource, post them to a SADI service, we get back a brand new graph. So this between the edges graph was created from nothing but the original URI nodes. And a quick way of explaining that is we just parse up the URI, right? We walk the steps, and every step is a whole new node within the RDF graph, and they're related and characterize themselves. And so from this transform of 212 triples, we've now produced 1,500 triples. So if that 212 is 10 billion, then we've got another couple orders of magnitude more of yes.
What's not clear is what the expansion is.
So we've got so we've got this Coley.net FOF RDF file, which is one of the nodes in Tim's FOF file. The transform is basically taking one of the nodes and relating it with a brand new relationship within the BTE vocabulary that peels off each step of the end of the URI and relates it to the next higher step. So that if you have a long URI with lots of steps, then you have a full, basically, hierarchy that explicitly expresses the implicit relationships that go into building out a particular URI.
So we're going from, which is the new piece?
New piece is the yellow down here.
Just that yellow piece. But that's
This one triple is part of the BTE.
That one triple is the second one from the bottom up there, right?
This one triple is derived from the existence of this node in the node list that was extracted from the FOF. So we have an extra order of magnitude in triples, and we have 3 times the number of nodes that we started with. And the point here is it's trying to scratch at the fact that well-designed linked data has a lot of thought that goes into the construction of the URI. And if we are able to draw that out explicitly, we can draw new inferences from that implicit information within the URI. This has a vocabulary, it's available in prefix, and it also has implementation on the DataFacts GitHub. So you can go try it out if you want. So why do this? Here's an example snippet from the BTE of Tim Berners-Lee's FOF file. And these 4 nodes would not have been related in the FOF file, and they're now related by a common broader within the BTE. And so, as a human looking at these things, so what? The point is that this is explicitly drawn out as an RDF graph that we can just reapply any of our RDF widgets to derive new information. Each of the nodes that we mint within the BTE graph are also annotated with the depths, going back up to the domain. So just so that you can, if you want to be able to write some Sparkle construct queries out of that, you can just quickly get at the depth without kind of walking the rest of the tree. And then here are four poorly highlighted nodes within the faux file, where we've actually constructed a whole new neighborhood of the four nodes that wouldn't have been interrelated within the original graph, but they are now interrelated within the BTE graph. So back to the question, 10 billion triples. Now what do we do? The BTE is one way that we can solve the problem by quadrupling the number of triples we have. The second is much more of a summary technique than the explosion technique of the BTE. And the concept here is that you take all of the REF triples in a particular graph, and you classify all of the subject resources and bin them into one of four bins on the left. You take all of the property, you take all the predicates that are used within the triple, and you can organize them within this middle binning, and all the objects of the triples you can organize on the right-hand side. So very, very commonly in RDF graphs, you get a lot of RDF type triples, and so you get basically a histogram here of the frequency distribution of the properties used within the graph that you're looking at. The three inner columns are colored in white, and because each of those are actually URIs, so they can be much closer connected within the graph. The farther you get out with the columns, they're darker gray, and so the darker gray are B nodes. So a lot of graphs have B nodes, and that's a telling characteristic of the graph itself. And then finally, the object literals stacked here on a histogram on the right-hand side. And then finally, the displacement of the left or the right aligns with the bottom and the top of the column stack to indicate that these particular subjects are source nodes, which means they are never referenced by another triple, and all of these resources or objects are sinks, which means they're never turned around to be described with another triple. So that's the concept of the classification of the resources that appear within a graph, as well as the triples of the relations between those nodes. You look like you're. Where are you?
I'm just thinking, why are you doing that? Why are you trying to balance the SPR?
I'm sorry?
So why are you trying to balance the SPR, try to classify them?
So what I'm trying to do is provide a quick overview of the entire graph in one single view.
So later, are you trying to efficiently do the query?
Right now, the focus is to communicate to a human observer the general structural characteristics of the RDF graph that you're looking at, both structural in terms of source, sink, and bridges, as well as subject-object reuse as subjects, and the vocabulary being used. Okay. So two real examples. Again, the 212 triples from Tim Berners-Lee's faux file, and another graph that I have been working with. It's 89,000 triples. One thing to note is that these aren't to scale. If the 212 triples were shown right next to the 89,000 to scale, it would be under my pinky and you wouldn't be able to see it. So I blew it up to compare it. So here you can see, because on the right-hand side, you have so many objects that are in line vertically with the predicate stack, and very few that are below the predicate stack. That says that all of these resources, not the literals, all the resources are themselves turned around and described as subjects of other triples, as opposed to the Tim Berners-Lee file. Most of the resources that are ever mentioned are never turned around and described again within the file itself. So we have, you can see that there's a lot of purple here on the objects of TBL, and a tiny amount of purple on the right-hand side. And what that says is that the purple is URIs. So there's a lot more URIs. Let's go back to the diagram. Sync URIs. So there's a lot more sync URIs than over here. You can also look at the difference in the predicate use. There's a lot more of one predicate than is used over here. And again, looking at the purple and red disparities, there's a lot of differences here. The commonality, the drastic change in gradient on the literals versus a very consistent use of literals in the faux file. Yep.
In the case of in Tim's faux file, the stuff below the predicate list, you said it's things that aren't described elsewhere in the file?
Yes.
Push back on that slightly. You mean they're things that aren't used in the subject of the triple elsewhere in the file, right? That could be used in the object position in a lot of other triples.
Yes. So by
And since you could
yeah.
easily flip a predicate, it's not that they're not described, it's that because that's like an artificial distinction, right?
Yes.
Like the direction of the triple.
Well, artificial is that one is and one is asserted and one's not, right?
Well, sure, but I mean, you could arbitrarily.
Yeah. So by described, I mean subject of a triple, not occurs in a triple. Yeah. So lots of differences between the two. So a lot of quick impressions on the distinctions. As I've conveyed so clearly, it's obviously not in every aspect is not intuitive. We're still kind of the color coding here is no decision process whatsoever. But I think once you get up to speed on how to decode this, I think it can be a pretty effective technique on a quick cut understanding of the differences among graphs. Okay. So here are these are hand drawn from actual data. So just a quick prototype to look at the different characteristics of a variety of different graphs. So you can see the interrelationships, the relative occurrences of subjects versus objects, the number of different triples properties used, the amount of triples used, and there's a big data set over here, which kind of dwarfs all of the other ones on the left. So you can get a nice graphscape of what's available to you across each of these graphs. So between the edges and the SPO balance are two overview techniques that I'm pursuing to give a quick impression for graphs. But once you get a quick impression and you start having some ideas of what you want to actually create, the Ben Schneiderman paper actually uses this quote that I thought was very inspiring, and I think is a nice segue into what I'm calling the visual strategies. And so it is, everything points to the conclusion that the phrase, the art of language, the language of art, is more than a loose metaphor, that even to describe the visible world in images, we need a developed system of schemata. So basically what I'm pushing towards is that the visualization themselves are represented in linked data as linked data. so that visualizations are just derived data subsets of existing data sets. So this is what I'm trying to push towards. So it's very hard to talk about data carving without also pairing it up with the abstract declarative visual strategy. And the blue here is the data carving, and the red is the abstract visual strategy. And so the point here is that it's a bottom-up process that's driven entirely entirely from the data, and you're actually working with all of the data at the same time. So this blue data carving would be the result of an interaction process with a particular user that began with starting a single node, and whenever they drop that node in, every RDF resource shows up right within that bubble. And until we establish some constraints for which particular graph subselection we want to create, we see all of it. And so from that single collection of resources, which is all of the resources, we would basically use the same SPO balance technique of seeing all of the predicates that come from it, come from any one of those resources, both direct assert as well as inferred from a variety of means. I'm focusing on using SADI to actually do that. But in this case, we chose the RDF type property among all of the properties that appear within the data set. And when we do that, all of the classes appear within the next bubble here. And then we've down selected it just to be organizations. And once we've done that, then only the organization, everything else kind of disappears. And we can reiterate that same process in a recursive manner so that we can then ask what properties come out of these particular resources. In this case, the has part relationship was available and it was inferred from, we know that from the dashed line. And we get all of the parts of the organizations. And then we recursively follow that out again to get the has part, to get another collection of bubbles. And we're establishing the data selection here. And then finally, rounding out to some literals for the latitude and longitude, and some parent features that themselves have latitude and longitude. So the idea here is that we're able to transition from a context-free, we literally know nothing about the data, to a highly contextualized view of the data that we're actually interested in. And while we get to that contextualized view, we actually get exploratory interactions by seeing the entire part of the graph that we're down selecting away from. So the data carving sits as a layer right above the data sources. So when we're getting all resources or all properties, we're just drawing from the current day Prizms of just querying to get what they are. The CSV to REF or LOD actually can cut down on that because it accumulates a lot of that metadata on which properties are used, give me a full list of the resources. All of those are re-exposed as version datasets themselves, so you don't have to just destroy the Sparkle query engine just to get this very common overview metadata. And there's a very tight coupling between the data carving and the abstract visual strategy, which is what I'll get to now. So this blue stuff on the left is the data carving that we constructed in a bottom-up fashion to establish the subgraph that we're actually interested in. And whenever we work towards creating the visual strategy, we actually elevate the blue layer up into the red layer to say that we actually want to visually encode the characteristics about those particular resources. And we can do that by dragging the same predicate tubes into the red layer, into different combinations of views that themselves can be described within a visualization ontology to things like scatter plots and geospatial maps. So in this example, we have this part of an organization that has an uptime and a cost, which are two quantitative values, and we're mapping them into a visual view, which is of type scatter plot. And this second view, we also have things that are latitude and longitude, and we're also incorporating the uptime. So if we had a map of, say, the servers that we have, we want to plot them on a map, and I want the color of the logo to indicate how long it's been up, or whatever. So you're showing those 3 dimensions within this map view, which is also typed to geomap. And because you're using an uptime, you're mapping uptime into this view, and you're mapping the same quantity into this view. That uptime characteristic actually exists at the intersection of those 2 views as a function of the data itself. We didn't have to determine that at any level in the visual because it's determined from the data itself. Because when we elevate something from the data carving up into the visual layer, we're actually minting new instances of visual elements that depict the data elements themselves. So when I draw a blue rectangle that depicts Tim Berners-Lee within his faux file, I have an instance of a blue rectangle that depicts Tim Berners-Lee. Or if I'm showing a dot at a particular XY within a scatter plot, I'm actually depicting the computer resource that has a particular uptime and cost. So the first step of the visual strategy is determining which subset of the data carving should be exposed exposed and encoded visually. And then once you've done that, you still have a pile of decisions to make about all of the different visual characteristics for those newly minted visual elements that depict data elements themselves. And this is actually inspired by Jacques Breton's semiology of graphics, which draws the distinctions between domain components as well as visual components. Breton was a cartographer, so he spent a lot of time figuring out how to draw the Earth on a two-dimensional plane. And there's a lot of nice perceptual and cognitive characteristics that fall out of making the distinction between planar components and elevation components. And so there's many more visual characteristics that you can attribute to the visual elements that you're creating. And I think each of those, I haven't actually done this part yet, but the rule for each of the visual characteristics really should just be a declarative rule, riff or something, that is a function of, that is basically applied to each one of the visual elements, that is just part of this whole visual strategy subgraph that has interrelationships with the other visual elements, all the way back to the data elements themselves. So if you need to know something about the data itself in order to determine the stroke color or the label or the fill color or its position or anything else, that's just part of the, it's all available within the graph to you at the time that you evaluate it. And we can also create some owl axioms on the class of scatterplot. That scatterplot has exactly one ordinate and exactly one abscissa. Abscissa, anybody?
Abscissa.
Abscissa, thank you. So, what I'm posing here is not just linked open data, but also linked open visualizations, where the visualization description is itself part of the RDF graph and is a first order citizen within the linked data itself. Yeah.
It seems like you have, as you're saying, a newly minted URI for the visual object.
Mm-hmm.
This is this new thing that's depicted on the screen.
Right.
The connection between that and the data that sort of describes. Is there still within that some sort of derived connection to what it actually represents? If I have some icon on the screen that is a tree, right? And I want to know what are the nearby trees. I have the URI which connects to the data, but how can I quite get at what actually represents the world?
Well, when you ground out to linked data in URIs, it's just back to the same problem of how do you connect this symbol, which is a URI for Pennsylvania, to whatever it means, and that's not a problem that we're going to be able to solve at any level, right? The second that you create a symbol, the semiotic says you still need some function to map it to the referent, and does anybody? I mean, for semiologically, you can't. I mean, that's just the foundation of meaning for symbols.
We could say that the newly minted URI has a reference back to the data that represents.
Oh, it's not a reference. It's a relation. There's a relation between the graphical element that I've created and the thing that it's depicting. And so when I say I'm depicting fof.rdf #I, that's what I'm depicting, right? I'm depicting the referent of that symbol, and it's up to the audience to determine the referent of that symbol, just like in any information system.
But I think so to have the connection that I'm talking to, perhaps that thing that you're giving the URI to is a contextualized version of the real thing. Are you pointing to in the ontology?
I guess I have to admit I haven't fully worked out how I want to relate the graphical element to the entity that I'm trying to depict. One could phrase it in terms of a prov specialization, just a more contextualized form of the entity that you're depicting.
Okay.
I don't know if I'm willing to go that far. I'm comfortable, and I can do, as far as I can tell, everything I want to do with just calling that relation depicts. And when I say depicts, its domain is a graphical element, things that are blue and rectangular or whatever, and I'm relating that graphical element to the thing that it depicts, whether it be Winslow or Patras or whatever concept you wish to convey.
So the cluster with the circles in it, what is that?
This thing?
Yeah, right below it actually.
Well, this one.
Between. On the left.
This one?
Yeah.
This
I
side.
know which one.
Hence the problem.
What?
Go ahead. Yeah.
Well, I mean, we can survive with not. I mean, we can never solve this problem, and we can survive by dealing with it.
Okay, well,
Right? It's fundamental to semiology to not be able to have a consistent function that maps symbol to referent. Right? That's arbitrarily invoked, if you will, upon every acceptance of the communication. Right? I mean, that's just. But yeah, there's a variety of ways that you could describe the relationship between this graphical element and the thing that this graphical element and the thing that it depicts. I don't need to go any further than saying that it depicts it, right? If I say this blue rectangle depicts Tim Berners-Lee, and you understand what that means, then I'm happy.
it's okay. We'll let
So, and then finally, when you apply these rules up the visual characteristic stack, you can actually use these rules to not only prescribe what the visualization should become, but once you have the final result, you can actually work backward and explain the visual characteristics using these rules that were used to derive those visual characteristics. So you actually gain some explanatory power by encoding these in rules, as well as prescriptive, constructive, generative power with those rules. And they're evaluated on each one of the visual elements that themselves are connected to the rest of the linked data graph of the things that they're depicting. So the final thing I want to just sketch out is provenance plus linkbacks. Again, centered around for Tim and his profile. So there's a URL there, and you can request it, and you can get an RDF file on your computer. And I can say that prov was quoted from that URL. And I can shove that RDF file through a prov activity and generate a graphical file. Here I'm using OmniGraffle, but it could be SVG or GraphML or choose your favorite graphical representation. And that graphical file was generated by the activity of visualizing the RDF. And hopefully when we generate it, or when we visualize that RDF, we're capturing some provenance about why we created that visualization, what resources we used to create that visualization. If I double click on this graphical file, I'm going to show you a bunch of lines and squiggles and letters that is the depiction of the FOF graph, right? So if I take that same graphical file that I constructed and I email it to each one of you, and some of you don't like people from Pennsylvania or Maryland, and so here in V1A, I deleted half of Tim's FOF graph, and here in V1B, I deleted the other half of his FOF graph, and then you sent it off and emailed it to other people. And now you have this huge revision chain of different artifacts that are tailored to whatever your particular task is, right? You needed to get rid of everybody who wasn't a graduate student, or you wanted to look at their salary instead of anything else. And so you're tailoring each of these views to suit your particular need, but each of those is kind of exists within this long provenance chain. And I mentioned earlier about the schematic of visuals. When you've done that, you've changed the message about what's being conveyed with each of those visualizations. And when you're the consumer of that final visualization, you might want to know what data remains, what content remains of what's available, or you might want to be able to construct a new visualization in some different way that's based off of the original data. So if we take that XML-based graphical representation and we sneak in a griddle transformation tailored to the particular graphical format, or you might just use RDFA, then you can actually construct an RDF graph right back from the graphical file format. And here is an example of some of the provenance that I'm encoding when I actually construct the graphical file format. And the red, again, is the visual, an artifact of the visual strategy. The green is the link back of the depicts that Patrice and I were just discussing. So this resource, whatever it is, has a color and a shape and whatever, it depicts Tim Berners-Lee. And so if we are able to grab all of those files that everybody edited and shared around and tailor different views, we would actually be able to see which ones of those actually still mention him within his own profile. And because this is his URI, we're tied back into linked data, and all of this is just more linked data at the graphical level that you might be interested in or not. And within these graphical elements, we can also, it's just RDF, so we can describe it how we wish. We can describe the provenance of those, the construction of each of those visual elements. We can refer back to the rule that was used to decide why it was blue and why it was a rectangle. We can link back to the original data file and the original code and whatever we need to if we want to talk about the visualization process that we might be interested in. And yeah, we collect up all of your edits of the different graphical file formats, and we're pointing back to all of the original stuff. And so we can get a much more comprehensive overview of the different data subsets that the community was actually kind of tacitly interested in, because it kind of persisted throughout all of those different graphical visualizations. And so when we kind of collect all that back up, and it's easy to get because we captured the provenance and it's available in query and like data and everything else. We get it all back, we griddle it, we get to see what data remains within each of those visualizations. We can start asking, of all the data that we have, which parts of those data sets was the community actually most interested in? And kind of a follow-on from that, if we know which subsets people are actually interested in, because that's what they're actually visualizing, then we can ask, well, given that we highlight all of those parts, we can start kind of making recommendations on what new subsets of the data should we be looking at, given that we know that they're interested in these particular data subsets. So again, a lot of benefits from promoting visualizations themselves as a first-class citizen as part of linked data itself. And I just wanted to kind of leave you with where I get a lot of my inspiration. I begin every one of my cognitive science yearly talks with this slide. These poor gentlemen this poor gentleman on the right is trying to figure out why the calendar ends in 2012, and he has a lot more context to understand and interpret the graphical depiction that the guy on the left made. But a couple millennia later, poor Calvin doesn't have the author, and he just wants to know why it ends in 2012. But we don't have to wait millennia for that, because we have the web, and people create artifacts across the web that we consume and run into, and we shouldn't have to try to perform a new archaeological endeavor every time we run into a new visual artifact. And I think with that, I'd like to conclude. Prizms is half done. I talked about all of the concrete widgets that we've thrown together. I've tried to contextualize where I see myself going with this work, situated within the type by task taxonomy proposed by Ben Schneiderman. And I think that the semantic web is in dire need of fulfilling those tasks that the visualization community established more than 20 years ago. I've offered a variety of techniques that I think help address this shortcoming, and I'd like to leave with you the proposition that we can have semantic recursion, that we can use the semantic web to familiarize, understand, and visualize itself by promoting visual artifacts into the linked data, just as part of any other data subset selection. And I hope that when I'm done with all of this, and hopefully more than just what I've kind of outlined here, that we can actually start using that as a concrete basis for developing a theory of visualization that really centers around this visual strategy of what rules, what context is needed, how should the visualization be constructed, how should it be reconstructed, which data should be used, which data should not be used, how should it be encoded, what visual characteristics apply, what navigation is performed, what does the user need to know. And I think that we can really start answering a lot of those questions and having a very concrete conversation. I'd like to have that within the visualization community, and I hope that this provides a foundation for that. So with that, I thank you for your time, and I'm happy to answer any questions. Thanks.
Questions for Tim? I have a question. what other approaches are people looking into? Are there other models? Not necessarily.
Well,
the same as-
within within all of this, or a particular.
But you've given sort of your, I won't call it an extrapolated vision, but you've sort of kind of gone long and kind
Yeah.
of and mapped out that whole thing, which is an important thing. It's taking us from where we have been, as you said, 3.5 years of work, and that's this little thing at the start.
Sure. Yep.
And but people have talked about some, automatic visualization.
Mhm.
And
Yeah, and I mean the biz community stopped talking about that in the late '90s, right? They just threw their hands up, and they're happy going through this system design, engineering, iterative. You tell me what you need, and I'll go craft something for you, and
craft something. No,
craft something.
I have to remember we're in the internet. So, but you have not used the words automatic visualization.
No, I did say generative, right? When you're able to specify the rules that are evaluated upon the newly minted visual elements to determine each of the visual characteristics, hopefully in an independent fashion, so that each one is a rule only onto itself. And when you evaluate those rules, you have in scope the focus of the visual element, but as well as the rest of the RDF graph in which that visual element is associated. And so I don't think that's just going to get you to the viz that you want, right? But I think that it is a start in helping you constrain the viz that you want. In that, well, I know that the region should be in this area, or that I know that it should not be red because I need to maintain a distinction between male and female, and the females are red, and so I can't be red because I'm a male, or I can't be placed next to this other visual element because the user requires a certain degree of visual disparity between the two. And I actually omitted it from the data carving, but one characteristic that I really like about the interconnection between the data carving and the visual strategy is that when you want to start to incorporate the user context and who they are, what they understand, are they colorblind, whatever, what path have they stepped through the application, or whatever is needed to be able to nail down what visual should be shown. I think that falls out immediately from just using the data carving, where you're describing the users themselves and you're describing the user state that you expect them to be in. So you just basically double the amount of data that you carve up, and relate the two as a function of this person needs to know about this particular data element. And when you know that they need to know about it, then you can use that as part of the rule. So you're steering the rules as a function of just more data.
So, kind of possibly along those lines, problems of data science, where you're taking data from different domains and bringing them together
Mhm.
to visualize, to reveal, help reveal concepts and lead to observations that weren't necessarily clear, focusing on independent domains. Okay?
So different vocabulary, right? Is
Well,
where
potentially.
you're getting yep.
Yeah, I mean, one example is this work of the Deep Carbon Observatory, where you're taking data from different areas of science,
Mm-hmm.
from volcanoes and earthquakes to first principles materials monitoring and everything in between. And the idea is to bring bring these together in different ways and create visualizations that we don't know how to do right now. I'm wondering how this, it seems like this might contribute rules that help.
Well, again, the rules are only. I mean, I've kind of partitioned the rules to only be at the visual characteristic level. I'm not putting. I mean, rules already exist in semantic web and at data level, and they have their place for it, and that's just let that happen, right? The only place that I'm using rules is at the determination of the visual characteristics of the visual elements that depict the data elements.
But okay.
So when it comes to rules to integrate across different vocabulary from different data sources, different linked data sources, so that right now, I've kind of scoped that away in assuming that I've done all of that work up front at my black layer of the prisms, made the coherent RDF graph. It is what it is. It's useful and interconnected and everything else. The one bit that I haven't quite figured out how to crack is, I had mentioned that when you do your data carving, you can select direct assert, which are these strong tubes, or the inference, which are the dashed tubes. Again, that inference I'm using Sadie to provide. You have to step out of this system to make that happen, right? Whatever your custom-made black box inference is. The one thing that I haven't cracked yet is basically how to specify the inferences that you want to derive within the data level without leaving this metaphor. And I'm not quite sure how to do that yet. And I think once you're able to do that, then you can pull from different independently well-constructed linked data sources just from different communities, and then fall out and integrate them with rules at the data level. But you?
I got a very interesting suggestion for you.
Okay.
Because I got them from they do something like computer vision where they try to detect the object inside a picture.
Mm-hmm.
And one of the problems they're trying to solve is try to figure out the relations between the different objects.
Yep.
But they haven't figured out the proper way to do that. But there's one thing which is called the image net, which is quite similar to the word net that we're kind of familiar with.
Oh, okay, cool. I didn't know about it. ImageNet.
Right.
Okay.
So that tries to describe the hierarchical relationship between different kinds of images.
So when two objects appear in the same image, this one always appears above that one.
Right.
Kind of.
Something like that, or tries to if you see a chair, then you see a furniture inside the picture. Something
Okay.
Like that.
Mm-hmm.
So if somehow we can try to visualize the entities, or try to map the entities to the object in the ImageNet, is probably one of the biggest contributions to the computer vision community, because that's what they are really. They want to figure out the relationships between the objects. Where in semantic web or the linked data, we kind of figure out a schema to provide this kind of approach. So if you have time, probably you can take a look at the ImageNet and try to figure out how do we map the entities to the real images or the objects, the real objects in the real world, such that people who are interested in the relationship between the objects can find the relationships according to our contributions, like the visualization of the linked objects.
So you're saying in ImageNet, they have chairs and furniture. You're saying if I happen to be visualizing chairs and furniture,
Or
I'll.
yeah, if you're trying to have an entity called chair,
Mm-hmm.
and you map that to the chair object in ImageNet, probably you can find some more links according to their database. and we can offer some more links like share.
Yeah, I mean, it's. I think it's clear that ImageNet has a semantics problem, and it sounds like a really interesting data set to expose as linked data.
Right.
And because it's visual,
I think
there could be some interesting interconnections between that.
Right,
Yeah.
so that can be another approach of really visualize the data because it's visualized as a picture or a photo.
Yeah.
So if you have time, just
Yeah. No, that's. Thanks for pointing that out.
Other questions for Tim? So let's, thank you.
Thank you.
Logistics man, if you haven't signed the log sheet, please sign it for our bean counters. Reminder.